And we're going to today cover two major topics. The first of them will be a coverage of partial functions within Scala. Partial functions provide a very powerful way of handling functions which are defined only over parts of their intervals. And they turn out to be really helpful in Scala in general, and in Spark in particular, in allowing us to conveniently process data where we only care about subparts of the data. And as such, there are alternatives to use of sort of filter and then map. You sort of do them together. It turns out that they are helpful for understanding certain Scala contexts, certain Scala constructs, and certain very helpful features of Scala. Because we have a bit of time, we won't be using all of the lecture for the second part. I wanted to cover that. The second major component of today's lecture is going to be about Scala ML and using Scala ML together with Scala with these partial functions that I'll have introduced in the first part of the class to accomplish some valuable processing. We're also going to see how we can, using pipelines, accomplish multifold cross-validation and learn more about the findings from our machine learning experiments through exploration of the pipeline sub-features. So I'm going to switch over to the screen sharing here. If someone could just double check per Iman's request, I'd like to make sure that the video is working today. Okay, and we'll try to go from there. I will try, moreover, to get a secondary recording going just in case we need it. So this would be Scala partial functions and collect and case. Okay, great. So here we go. Hopefully that won't adversely affect my performance too badly. Okay, so what I want to cover in this first component is the use of partial functions in Scala. Scala partial functions are extremely powerful. The Scala language provides special support for partial functions. So they're kind of built into the language syntax, how we use them. And they provide us with a very convenient way of accomplishing certain types of tasks. We're going to take a whirlwind look at this, bearing in mind we're not looking exhaustively at these topics, but it is an interesting topic, and it will help explain the second part of today's lecture in Spark ML. Some elements of that. Okay, so a partial function is a function from a domain to a range. So it might be a function that, for example, maps ints to doubles, or it might map strings to ints by looking them up in a dictionary, or strings to doubles by taking their square root, or by converting them to the reciprocal or what have you. So a function in general maps from a domain to a range, and a partial function is a function that's only defined over a subset of its domain. So maybe, for example, we're dealing with the square root function as applies to reals, and square root, unless we go into the complex number domain, is only defined for real numbers as its domain, the numbers to which we apply it, if they're greater than or equal to 0, right? It's not defined for numbers less than 0 if we're staying purely within the real numbers. Similarly, log is only defined for things greater than or equal to 0 for real numbers. And if we think about a divide by function, or better yet, is a reciprocal function, that might be a more natural one. Divide by would be another. Those are defined only for certain elements of their domain. What is reciprocal defined for? For reciprocal, it means 1 over the argument. Well, be defined for things that are not 0. Okay, and if we're thinking about taking 1 over a double, it's for things that are something other than 0.0. Divide by, similarly, it might, the function divide by might divide some fixed number, say 1,000 by whatever we give it as an argument, and it's not defined for 0. Okay. Now, it turns out partial functions, as I noted, enjoy special support. They enjoy special support in terms of language semantics and the built-in syntax for the language. So we've been talking about partial functions in general as a construct. I'd like to now talk about definition of partial functions as supported in Scala. And specifically, Scala has a construct. It's a type parameterized class called partial function. Okay, and partial function is a trait in the Scala. It's a topic we haven't had time to cover specifically, traits, but they are useful for sort of classes that can be mixed into things. And a partial function of A comma B, where A and B are types, and so this is type parameterized by the type, by the 2 types involved. That represents a partial function whose domain is drawn from A and whose range is drawn from B. Okay, so for example, if we were dealing with something that's reciprocal and it takes a reciprocal of integers, A would be int, B would be double, right? Okay, so this conceptually represents a function that goes from A to B, but it's a special type of function in that it's only defined over a subset of its domain. Now, a class that fulfills this trait, that satisfies the needs of this trait, has to define 2 methods, not methods, methods. Okay, methods. The 2 methods it must define are apply and is defined at. So the latter is probably pretty clear. Given this partial function, we could say, hey, are you defined at 0.0? Are you defined at -3? Are you defined at plus 1,000? Okay, so a partial function has a certain range over which it's defined. Outside of that range, it's not defined, and we can interactively give elements of a certain part of its domain under which it's defined, and we can give elements from its domain, particular elements, particular, say, numbers, particular strings, and say, hey, are you defined for this? The other component is this method apply. This is also a method that needs to be defined. And the applied method captures operationally the application of this function to an element of its domain. Okay, so you recall a partial function is a function that's only defined over a subset of its domain, and it maps that subset of its domain to a range. And here we're performing that mapping with apply. Okay. Very importantly, if it's not defined for that, apply doesn't guarantee any specific behavior. It could throw an exception. So we should only be applying it to things for which is defined at is true. It's actually defined there. Okay. So we shouldn't be applying a reciprocal function, something that takes 1 over the integer given to it at 0. We should first find out, okay, is it defined there, defined at that point? And if so, then we can apply it. Okay, so it allows the function to be applied and to map it to a range. Okay, so I'd like to define some partial functions, okay, in Scala. Now, normally I would fire up the Scala shell to do this rather than necessarily going all the way to use Zeppelin. But I know you folks probably, some of you only have Zeppelin installed. And so why don't we go create a notebook in Zeppelin, okay? So if we go into Zeppelin and we do create a new note here, I will say partial functions, partial functions, partial function exploration. Okay, and we will use. We could use Spark. It's probably not the worst thing to use. I wish we could just use Scala, but I don't see that as a choice here within it. Am I missing it down at the bottom here? The last one I see is pig. Yeah. Okay, so there's no Scala. Okay. What we do then is just to use the one we've been using from last time. Do you guys still have that around? That one from last time? We're going to be extending that. And if you want to go into that, you could start using it. Otherwise, what I'm going to do is to, I'll go ahead and do that too. Okay, so here we go. Boom. This is the March 27th lecture. This is in Spark as the default interpreter. Okay, so it's the Spark interpreter within Zeppelin. Alternatively, if you were interested, you could fire up the Scala shell if you have that. Okay, so ladies and gentlemen, we're going to experiment some with partial functions. And just to get something out of the way that we'll be needing in a couple of examples, I'd like to do import scala.math.underbar. This is going to import a swack of different math functions for us. Things like square root and things like the sine function and other types of mathematical operators like floor and ceiling, etc. Okay. So we're going to define a partial function in two ways. The first way we're going to define it is as a class, okay? So we're going to have a partial function square root 1, okay? We're going to be defining square root explicitly as an analog to square root as a partial function. So I'm going to go paste this in here, but the basic deal is that we're going to say, okay, we have a val. It's going to be an instance of the partial function trait mapping doubles to doubles. So its domain, thing from which it maps is double, and the thing to which it maps is double. It's a square root of double precision numbers. Okay, and it's going to have two elements. These are exactly correspond to the elements I just mentioned before that have to be defined. Apply and is defined at. So apply takes in a double, and it maps it to a double just by calling square root on it. Is defined at takes in a double, and it returns a what? What does is defined at return? It returns a Boolean, and the Boolean indicates whether or not the partial function is defined there. And in this case, we want a partial function that's defined only for double precision values greater than 0.0. Okay. Great. So I'm going to define that, and you'll notice that I get back an instance of a partial function. It's something that is a partial function. It turns out it's also a function. The fact that I define apply allows me to take that function and apply it to a number. Okay. So I could apply it to, well, let's do a 2.0, right? And we get back to golden ratio. Here we go. So I have an apply, and the apply operator just applies, it defines what happens when I call it on, in this case, a double, right? That's what apply does. Unapply takes it apart into its constituent pieces. Apply applies it to the pieces necessary to make it up and gets out a whole object. So here we are. We've applied it to a particular number. Now, if we did partial function square root 1 dot is defined at 2.0, what do you think we'll get? Yeah, we'll get a thing that says true. What could I enter that would indicate false? Say -2, right? -2, yeah. And it would not be in its legal domain. It's not defined for it, so it'll say false. Okay. Simple idea. Here it consists of two methods. And we can use this. And it turns out that some libraries in Scala make use of partial functions, but what's more notable is the built-in support provided. Well, we're going to see specifically the case of collect makes use of it, and that's what we're going to be using. Fortunately, you'll be happy to know that there's easier ways to define partial functions. And the main easy way to define them is using the case construct. Now, we've seen case before. Where did we see case before? Anyone remember? We saw it in matching. We saw it in matching, where we're matching a set of possibilities. I don't know if you remember that, but we saw things like this. So you can do expression match and handle different cases. And this makes it look almost like just a different version of the C or Scala or Java construct. But in fact, you could do much more interesting things. You could do things like this: case X if X even, case X N if N prime, case N if N square. And it turns out we could do more interesting things yet with regular expressions, and you can define a regular expression, match a string, and using the regular expression, it extracts each of the parts that it matches, which is really cool, because then you can have an expression involving day, month, year. It's extracted them from string by virtue of matching them. So when we have case expressions in Scala in general, we use them to we often use them to match up the characteristics of the thing given which is being matched, and to extract pieces from them. How these pieces are extracted is via unapply. I don't have time to go into that a lot, but it's via unapply. And you'll notice it can do it for various special cases. Like here, it's saying, okay, if we have something whose year is 1999, then we extract the day and month for that, and we'll handle that case differently than one involved in the year 2000. So we can actually do quite sophisticated things. So those are where you've seen case constructs before. But the truth is that all of those are working by virtue of the fact of defining partial functions. So each of those cases, each of those instances of case, each of those cases of case, if I wanted to abuse English, each of those was defining a partial function, okay? And partial functions are automatically created when you do case of something or other, okay? So let's go define the same function again, okay? Using this built-in support via the case construct. So here we'll go. We'll do val pf square root 2 equals, oh, sorry. We have to actually state a type here. As we'll see, it's actually rare in day-to-day use of it that you have to state a type when using the case construct version of it. But you do sometimes have to. And in this case, we're defining a method, defining a variable, a value that uses it. We have to say, hey, it's a partial function. And what is this thing? Well, you'll notice all we do is we do this. We say case x if x greater than or equal to 0.0, then we define square root of x. Okay, so I'll put it up there on the bigger screen. Case x, if x greater than or equal to 0.0, we define this. So here we're saying, hey, for case x, if x is greater than or equal to 0, then this partial function square root operator is defined as square root. Notice what we're not specifying. What are we not specifying here? What are we leaving out? Yeah, like what to do if it doesn't match this. And this is exactly the point. Here, this case construct defines a partial function. You've delineated what are the different cases that are handled, the different instances of partial function that are defined. And if it doesn't match one of the cases, guess what? It's what? It begins with a U. It ends with a D. Undefined. It's undefined. Okay. So if it doesn't match one of the cases, it's going to be undefined. Okay. That is sort of an automatic element of this here. So let's go take a look at that. Here we go. So this defines a function, and I would claim to you that it's going to automatically know how to do is defined at. So we'll do is defined at minus 2.0. We'll just do the same one we did earlier, and it says false, right? Is defined at 2.0. So at minus 2, it's not defined at 2.0. It is defined. How does it know that? Well, it runs this and it sees, okay, was it caught? If so, no. Now, secretly, I believe what's going on under the surface is it's using an option and it's determining, did it return none or an actual sum value, and using that. And in fact, you can readily lift. If you do like a lift of, okay, and I've got to be careful with this. I haven't used this here, but I believe you can do something along these lines. Okay. Yes. Okay. So let's just see. Okay. I may have to withdraw my example here. Yes. There's a way you can directly lift this into into the domain of mapping the input to an option of the output. And I'd have to go back and find out where it is we call lift, but I think it might be we call it, sorry. It's this, but it gave an error. Oh, I don't know what. I used parentheses. Okay, bad. I was a bad boy. Yeah. So it mapped it to a function that goes from doubles to option of doubles. Okay. And in fact, there's an unlift that will take functions that go from X to double of, or from A to option of B. It will take it into a partial function. That's another function. That's another issue. Okay. So, ladies and gentlemen, we see that we can define automatically this partial function using this case construct, which is really nice. It's even sweeter how you can use it in day-to-day experience, because you don't need to give one of these long declarations. You can just use it along the way. So here we have partial function of that. Now, if we do partial function of this, what happens? Do good things happen? Do flowers blossom and birds chirp? No, it becomes unhappy. It actually throws something. Because remember, a partial function can only be applied to things for which it's defined, for it to be defined. And outside of that, its behavior is not defined. It's not specified. So you're just asking for trouble for doing this. You should really be asking, is it defined? Okay, there we go. Cool. Excellent. Okay. So why am I going into this now? Well, it turns out we're going to be using partial functions. We're going to be using partial functions, and we're going to use them in an extremely common case where partial functions are used. It's not the only one, but it's a very common one, perhaps the most common. And it's using a method which we haven't used yet called collect. Okay? The collect method, conceptually, you can crudely think about it. Maybe it's not so crude, actually. It's not a bad approximation as giving you what a combination of filter and map would give you. Okay, it's kind of like in a single function call, being able to both filter the input to just those things that are for which your function is defined, and then map using that function. Okay, so normally, let's go take a vector here. we'll take a vector of, and just so we can see it very clearly, we'll do this, and you know, something along those lines. We could actually produce that automatically through a call, but that's not bad. Okay, and suppose we wanted to now here apply square root to the numbers that are 0 or more. How could we do it with traditional filter and map? Can anyone tell me? How do we do that? We want to apply square root to those numbers for which it's defined. Otherwise, we just won't include a value. What could we do? Yeah, filter to include just those things which are greater or equal to 0. We could also ask is positive. It's another one, and then we map by taking the square root of them. Right? Here we go. And through type inferencing, it's able to figure out the requisite types for these guys, and it can do that. Right? We're comfortable with that? Okay. Well, it turns out collect will allow us to do the same thing, but in a more elegant way conceptually. Because basically we're going to apply a partial function here. Okay. We're going to call collect. And what we're going to give collect as an argument is going to be exactly the definition we used earlier. Now, yes, we could have just passed in pf square root of 2, and maybe I'll do that here just to show pf square root of 2. Here we go. Boom. Mumble. Okay. Okay, this is for method collect. Do I need, is this a case where I actually need this? I can't believe that. Yes, it is. Okay. Wow. Okay, well, I'll be, okay. Here we go. But alternatively, we don't have to define this ahead of time. We could just say collect, and we will actually use what we used for the definition of PS, this guy here. We can copy that, case X, this guy here, and there we go. And it will do the requisite type inference here, okay? It realized, okay, X here must be a double, and therefore this must be a partial function from doubles, and it says, oh, it's returning a double, so it's a partial function from double to doubles, okay? You'll notice what this did. It did exactly the same thing as this filter here, right? Precisely the same thing. Filter and map, rather. Filter and map successively. But it did it all in one sweep. In particular, what did it filter out? What did it filter out? It was filtering by what? Put it positively. What things did it keep? Things for which what? It was defined. This function was defined. And it just discards those for which it's not defined. Okay? So here, I say it's like performing a map, filter and map at the same time, because we're filtering out things for which it's undefined, or we're only retaining things for which it's defined. We're only applying it for things which it's defined. And then we're mapping according to it, right? We're taking the square root. Does that make sense? Okay. So this is the collect syntax. Now, I could go into a lot more detail here about how partial functions are used together with match to accomplish things. And I would say that if you're working with strings, particularly regular expressions within Scala, you really want to make use of the case constructs, these partial functions. You know, if you're dealing with matching regular expressions, I mean, it's just a thing of delight. You can define regular expressions just like this, and then you can match them in match different subparts of them and extract it and work with it. It's highly recommended. It turns out regular expressions are really well supported within Scala, and they're supported not only with this syntax. You'd say a string. This is a raw string. That's why it's in 3 triple quotes. Or you could say raw before just a regular double quote. And then you say .r to indicate it's convert it to a regular expression. Alternatively, regular expressions in Scala are indicated using a construct. You can use a little bit like sed, the sed construct. So if I wanted to have, RE1, one way to do it is I could say, just raw foo.r. This is a regular expression. There we are. Another way we could say it is with triple quotes around it. That obviates the need to say raw. This would be RE2. The final way to say it would be with val. I've got to get the syntax for this right. It's a little bit tricky. I think you could basically just say foo, foo here, and then you can say sort of the mumble. I've got to. I thought that was the correct syntax, but I'll have to look it up. In any case, you can define them using this sort of slash syntax very, very sweetly. So when we have regexps, we can define them, and then we can take them apart using this and match things within them. And that will allow us to handle the cases where this regular expression matches. So for cases where this particular regular expression matches, we can extract these things, for example. Okay. So I am now going to switch. Having covered the basics of these, I'm now going to switch over to our next topic, which is going to be using these in the Spark ML context. Okay. So pardon me while I just stop this recording. Stop both recordings. And we are going to then go and move over. Oh, was I screen sharing?
Yeah.
Okay, I wonder what this present to everyone is. Then curious. Okay, well.